Okay, in example 2, we're going to just repeat this whole situation, the whole process, except this one's a decay, but you'll see where the question's virtually identical. So in this case, the half-life of a radioactive substance, this case it's plutonium 210, is 140 days. Now, that right there is telling us a bit of information. That's where we're going to use our snapshot. A sample of this element has a mass of 300 milligrams. Its decay is proportional to its size. So again, that statement at the end tells us that this is the E function we're going to use. So again, we have everything except for the proportional constant. We need that K. That K is specific to each question. So in this case, we have to figure out the K, and we use a snapshot to do that. Now in the last question, we had a snapshot 3 hours from now. This one, we actually do have a snapshot by it telling us the half-life. So we know the snapshot happens 140 days from now. And we actually know how big the substance is 140 days from now because it is 300 milligrams to start. So half of 300 milligrams is 150 milligrams.
Jamie McLennan, come to the main office, please.
So that's going to be our snapshot to get our proportional value, or our K. So we're going to use the same equation. The fact that it's decaying will be considered in the K value. The C is 300. We start it with 300. The K, well, that's what we got to figure out right away. We'll use this particular snapshot to get the K. So in this particular snapshot, we're talking 140 days. And the Y at 140 days is half of the original, so 150. We'll plug in this information into our equation. So 150 equals 300. E to the K and the T is 140. We need to isolate just like we did last time. So first we'll divide by 300. So this side is 150 divided by 300 is of course a half. And again, this is why it's a decay. So we're going to get a fraction here. E to the 140K. To gain access to that K value, to isolate, we need to take the ln of both sides. Ln gains us access to the 140. Oops, 140K. Ln E. Ln E is 1. So we're left just with 140. We'll divide that. So it's ln a half divided by 140 equals K, or the way we like to write it is 1/140th ln 1/2 equals K. So our equation then for this particular case is Y equals initial value of 300, E to the proportional constant, which you're going to have to practice writing small, or better yet, take up some space. Don't try and cram it up in that exponent. It's going to get too crowded. And I've seen too many cases where people just couldn't read their own writing. So you'll see I'm using lots of space. So that plan is exactly the same as it was before. We have a snapshot. We plug that snapshot into the function to get our unknown K value, our proportional constant. We take the ln of both sides to gain access to the K. We now have a K value. We can now go off and answer any questions. So step 1 is always the same. Get the equation. Get the K value so you have the equation. The rest is just like what we had before. So if we find the mass at 50 days, you can do that. I'll actually give you a sneak peek. Second question, same thing. Find the rate of change at 50 days. So that's where you'll differentiate. And then question 3, well, we're not going to do question 3, might be if I tell you how much polynomium there is, you could tell me when, how much time has passed, but we've skipped that. So we'll ask the supply teacher to pause here and give you a chance to try these on your own, and then we'll come back. So hopefully you've had a chance to try these on your own. I'll do them here. It's at 50 days, so I'm going to add in the 50 right here. T equals 50. Again, this is really an exercise on your calculator. Take the ln of 0.5 if you wanted, get an answer, divide by 140, get an answer, multiply by 50, get an answer, do e to that answer, multiply by 300, and hopefully you got 234.2 milligrams. So remember, this tells me find the exact mass after 50 days. So there's how much we have left. The second one asks us to find the rate of change at 50 days. So we'll need to differentiate.
Please come to the main office. James Brooks to the main office.
So we take that same original function, but now we're going to differentiate it because we want rate of change. So good news is, it's just like before, it's a plain old e function with a coefficient, but we know the derivative of the e function is itself. So the 300 e to the 1 over 140 ln 1/2, all that stays the same, times the derivative of that exponent. And that exponent, even though it looks nasty, is really just a coefficient in front of t.
Brand new school clothing is on sale outside the student council office. Please see Mrs. Van der Bosch to buy new school clothing.
I don't know if you can hear the announcements going on, but welcome to say hi to Miss Wanamaker. Anyway, back to what we're doing here. The derivative of this is itself times the derivative of the exponent. The exponent is really just like a 7t. So the derivative of 7t would be 7, except instead of 7, it's this number, 1 over 140 ln 1/2. And now we can go off and sub in 50. So we've got 300 e to the 1 over 140 ln 1/2 50 times 1 over 140 ln 1/2. Punch all that in your calculator, and we're going to get a negative 1.16 milligrams per day.
There is a meeting for all members of the...
So we might take a second to pause and be curious about why it's negative, but if you think about it, remember we're talking about decay, so the rate of change must be getting slower, coming down, and that's why it's negative. So that's 2 examples there for you to consider. You now have a worksheet on exponential growth and decay, which I have asked the supply teacher to pass out. And just follow the same process here, find your K values, answer the questions, and you should be in good shape. Thanks very much.